Magnets are truly amazing. Young children can find delight in the miraculous power of a magnet to pick up paper clips. Parents use magnets to hang their kindergartner's latest watercolor masterpiece on the fridge. Giant MRI machines allow doctors to peer almost magically inside our bodies. Even some superheroes and supervillains harness the power of magnetism. Today, we explore several magnetic sensing technologies and get some guidance from Littelfuse on how to choose the best magnetics to solve our engineering problems. This edition of Tech Chat is sponsored by Mouser Electronics. I would like to welcome Julius Finkus of Littelfuse to our Tech Chat. Julius, why don't you kick things off by introducing our topic for today's chat?
Hello, Dale. Thanks for introduction. Yes, so I would like to touch base the magnetic sensors mainly and where and how they are used in the applications in the market and what would be the best option for customers or engineers to select the technology.
Because of my primarily analog background, I always enjoy learning about sensors and their applications. So I'm really excited to get started with you, Julius. But before we do that, why don't you introduce yourself to our audience?
Yeah, of course. So I'm Julius Venkos. I'm Global Product Manager of Magnetic Sensors. I joined Littelfuse as a design engineer of automotive sensors back in 2008 and later moved to sensors business development where I spent more than 4 years in this role. And currently I'm covering the product management role.
All right, thanks for that background, Julius. Now, why don't you give us an overview of the upcoming discussion topics?
Okay, yeah, the key topics covered today are a brief technology overview, and then we will dive deeper into the features and benefits of read, Hall, and TMR. We will compare each of their attributes and how those fit into various applications. And lastly, we will talk about read switch as a core technology of Littelfuse sensor products.
That sounds great. So let's go ahead and jump then into topic number one.
Okay, so in these days, whenever we use any device from big appliances like fridge, washing machine, as well as wireless security systems or tracking energy, water, gas consumption, it has user presence, environmental conditions, proximity, or flow detection capabilities. All these features are enabled by various kinds of sensors, technologies, which makes the application smarter, interactive, and efficient.
So that suggests that we probably have lots of magnetic sensors already in our home or office or factory environment, even if we don't know it.
Exactly, exactly.
And so before we go on, then I'm curious. So, what are some specific applications just to kind of whet our appetite for a magnetic sensor in, say, the robotic vacuum or it looks like an espresso machine?
Yeah, so the robotic vacuum cleaners they definitely are enabled with various types of magnetic sensors. As well, we have also, as I mentioned already, the washing machines or fridges for the door position detection. So that's also where we are using the sensors, or customers they are using the sensors for.
Excellent. Now, I remember learning about Hall effect magnetic sensors back in my EE courses in college. It's been a few years, so we won't talk about how long, but you have other types of magnetic sensors as well. So, give us a deep dive into the operation of these different magnetic sensors.
Of course. So yeah, so as we agree that I'm going to very quickly explain the operating principles of the three different magnetic sensor technologies Littelfuse offers today. So I would start with a reed switch, which is a pair of ferromagnetic reeds in a hermetically sealed glass envelope with an inert gas inside. The reeds will close when a magnetic field is applied in its operation lobes. When looking into the Hall effect, sensor is a solid state device where the output voltage is directly proportional to the magnetic field perpendicular to it. It's available in both digital and linear outputs. And TMR sensor is also a solid state device where the resistance changes proportionally to the change in the magnetic field. It's also available in both digital and linear outputs.
All right, thanks for that introduction. And that's an important point there for people that, you got the digital output for the two on the right, and then also the analog or linear response. So there's a lot of different ways you think can use these sensors.
Of course, yeah. So definitely, these also provide some benefits and features for any of applications, which is the technology itself can be selected accordingly. So reed switches are unique in that they require zero power to operate. This makes them suitable for ultra low power battery applications, They are also unique in that they are capable of carrying a load of up to 100 watts, so they can switch power level type loads. They are available in various sizes and configurations, and they operate in all X, Y, and Z directions for the most mounting flexibility. While Hall effect is a solid state device, it has no moving parts, which makes it suitable for high shock and vibration environments. Also, it is reliable up to billions of operations due to not having any physical wear out mechanism. The output can be both digital and analog, which makes it suitable for angular, position sensing, and high speed switching. The typical packages are TO92 for leaded and SOT23 for SMT. And another one is TMR is also solid state with no moving parts, ideal for high shock and vibration environments and long operational life. It's also available in digital and analog output like Hall. TMR is unique to Hall in that it requires significantly less power to operate and it's the most sensitive of the three technologies, which means it requires the smallest magnet to operate.
Now, maybe this is coming later, but for the reed switch, what does NO, NC, and CO mean? I'm not familiar with those terms.
Usually that's like normally closed or changeover abbreviation used in the reed switch or magnetic sensors world.
Oh, okay. So if it's normally open or it's normally closed, and
Mhm.
then interesting. Thank you. Now I peeked ahead, but on this next slide, you provided us with a handy comparison chart showing the key applications side by side.
Yeah, so definitely. So starting at the top, reed requires zero current to operate, and the Hall requires the most. TMR and reed are significantly more sensitive to a magnetic field than Hall, although TMR is slightly more sensitive than reed. All three are available in digital outputs, whereas Hall and TMR are also available in analog, which I also mentioned before. While looking into the sensing direction is important because it all allows for mounting flexibility, reed switch is the best here as it can detect both the north and south poles of a magnet in a full three-dimensional space. So as I mentioned before, a reed is the only of the three technologies which can carry the loads up to 6 amps and 400 volts, depending on the size. Because of its capability, reed also does not require external components for ESD protection. In very high or very low operating temperature, you will get the best performance from reed, but Hall and TMR are still good options. While for the high speed switching applications above 1 kilohertz, you will want to choose Hall or TMR, such as gear speed sensing. TMR and Hall are available in SOT23 very small packages, which gives them a size advantage to read. Also, since Hall and TMR are solid state devices with no physical wear out mechanism, they have an advantage in high shock and vibration applications. From a component cost perspective, if you look into the bottom of the table, Hall is going to be the most cost effective. However, it will require the least cost effective magnet to operate because it is the least sensitive of the three technologies.
This slide's really an interesting testament to the ingenuity of engineers. You've got the same physical phenomenon, a magnetic field, and these massively different devices that all respond to that magnetic field in a different way and solve different problems.
Yes, correct. Yeah, exactly.
So take us full circle, Julius. We see these three different magnetic sensor types. They've got pretty different specifications. Help our engineering audience pick out the right sensor to solve their application problems.
Okay, so now let's translate the attributes, features, and benefits of each technology to real world application examples. So, moving forward, for battery powered door and window position sensors, reed is the best choice due to the zero current consumption in the off state. For non battery powered position applications, such as lid detection in a small appliances, the reed switch is still an excellent choice because it has the most mounting flexibility due to it being omnipolar and ability to sense in the X, Y, and Z directions. Readall is also a two-wire device, whereas Hall and TMR are typically three wires. So in applications such as refrigerator, door open-close detection, where you may have a long leaded wire harness, there might be significant added costs due to the extra wire and the potential overvoltage protection needed if using Hall or TMR. For continuous flow rates, such as the inlet in a tankless water heater, Typically, customers will prefer Hall and TMR due to the faster switching capabilities and the smaller package. For counting, such as gas or water meter, the reed is an excellent choice, again, because of mounting flexibility and zero current consumption. TMR can also be considered as a good choice here. While for single point level sensing, for example, a washing machine detergent level sensor, where you just want to know if the tank is empty, we will lead with read as the technology of choice for similar reasons as non battery position applications, mounting flexibility, and being a two wire device. Now, for multi point level sensing, for example, an automotive fluid level sensor where there could be dozens of points of level measure, the read has even more advantages over Hall and TMR. As an example, each Hall and TMR requires a capacitor and potentially other components for protection at each measuring point. When a typical fuel level sensor has 25 points of measure, you are looking at potentially 50 to 100 more components on the PCB using Hall or TMR. It's the reason that we see reads ladders very common for multi-point level sensing. And last, relay applications such as automated test equipment or audio amplifiers. Reads is the only technology used here. Hall and TMR won't be considered. So as you can see, all three technologies have their own advantages with reference to applications where they are going to be used. Design engineers have a freedom to select the most suitable technology provided by Littelfuse for their end products.
That's really helpful, and it reminds me of my earlier comment that we all probably use magnetic sensors every day without knowing it. For example, I hadn't thought about having them in my car.
Yes, exactly. So that's definitely the application where the most of the sensors would be used.
Yeah. The other thing is this slide is really helpful, I think, to our audience in that if even if it's not solving the exact problem for them, it's giving them an idea of something that's probably very close to what they're going to do and it'll help get them started.
Yep, correct. Yeah.
So what do you have next for us today, Julius?
Yes, so today I would like to discuss a bit the reed switch technology. So you would ask why reed? The reason is that Littelfuse is the leading manufacturer of the reed switch and reed sensors globally with long history and deep knowledge of the products. So reed switch technology is considered as a major technology. The reed switch has remained as a popular choice for low power applications because of its simplicity and reliable performance. Reed is an electrical switch operated by an applied magnetic field. The switch consists of two or three thin metal pieces called reeds with sputtered contacts and their tips that are spaced a small distance apart. The reeds are typically enclosed in a sealed glass tube filled with inert gas. A field from a magnet or an electromagnetic a magnet deflects the reeds, making or breaking the switch contacts. So as you can see in the left corner picture shows the various components of the reed switches, which I discussed about. So how do we characterize the reed switches? We put the reed switches into a test coil and apply current. The current creates a magnetic field inside the coil. The more current, the stronger the field. We increase the current. The level where the switch closes is called the pull-in or PI value, the same abbreviation. We then have to decrease the current to let the switch open. The level where the switch opens is called the dropout or DO. The pull-in and dropout are measured in units called ampere turns or in shorter form AT. The AT units only have meaning in this particular test with a particular coil. There are industry specified coils with certain sizes and numbers of turns of wire. If you change the test coil, you change the measured pull in and dropout. So there's no simple way to correlate AT and magnetic field from the magnet. So to summarize, reed switches are magnetically operated. The magnetic units used are ampere turn, pull in the AT value at which the contact closes, drop out the AT value at which the contact opens.
So since there's a difference between that pull in and the dropout, that's basically hysteresis. So this reed switch is kind of inherently debalanced. Is that correct?
Correct, yes. So there is some, I would say, different distance when you need to open the reed switches because of the hysteresis here. Correct.
Now, ampere turn, that's kind of it's a weird unit. Why don't they use something like Gauss for defining how much energy it takes or the strength of the magnetic field?
Yeah, each manufacturer, as I mentioned before, that the industry itself is basically related to the coil which manufacturer of the reed is using. So the Gauss level is more associated to magnet itself or actuator, while the reed switch we can measure by using the coils in AT values.
Oh, that's interesting. I've never heard of that before, so that's fascinating.
In this slide, which I like very much, I would like to share with you the importance of magnet or actuator orientation towards the sensor. As you can see, the moving part is actuator and the reed switch is shown as a green bar. The round green circle is activation zone when the contact is closed, and yellow is release of contact area. As you can see, the first activation is done by single pole with linear motion at the end of the reed switch. The reed can be activated either with north or south pole, or with both as it's represented on the following picture. The magnet should be centered towards the reed sensor and linear motion activates the contacts. In the metering or flow speed as well, the magnet can be revolved on the axis, and by approaching the end of the reed switch, contacts are closed as well. The last activation option we call Furious Vane, where the stationary magnet holds the switch contacts closed and the ferrous metal or anti-parallel magnet moves closer to open the switch. So I hope this slide gave some understanding on the magnet orientation towards the reed sensor.
So, what's an example of that? The ferrous vane. Where would somebody use that in an actual product?
Yeah, so as an example, that could be like seat occupancy for either cars, electric cars, or vehicles or trucks. That's where the seat, comes into with this furious vein or part and disturbs the magnetic field, which is created by an actuator.
Oh, okay, that makes sense.
After a brief introduction of magnetic sensor technologies, I would like to present the Littelfuse sensor product line. As I already mentioned, Littelfuse is a leading manufacturer of reed switches and reed sensors. Therefore, bare reed switch is the main product provided to the market with extensive sensitivity range and lead forming. In addition, overmolded reed switches with enhanced mechanical robustness compliant to ATX, UL, and are available as a PCB mounted product. The next reed-based product family is the reed relay, operated by low power in the coil, used for the power switching applications. As well, a standard sensors assembly is based on the reed and hole technology packaged into cylindrical flange mount type housing with standard sensitivity and harness length selection. The last product family is the TMR switch in SOT23 package and is available as bipolar, omnipolar, and unipolar types.
So, I don't think a week goes by on this job when I don't hear about another industry standard. But ATEX is a new one for me. So, what does that cover?
That's a product which is compliant to the explosive environment requirements. And ReedSwitch itself is ATX compliant component because of the glass sealed contacts. And there's no arcing possibility, which is a concern for other products usually in ATX environment.
Oh, excellent. Well, that would seem to be pretty important, and I haven't worked much in explosives, so that explains why I haven't heard about it.
Correct. Yeah, you're lucky.
Yes, but I'm glad that it's out there. For our viewers that would like to get more information, what's the best place for them to go?
Of course, so don't hesitate to visit our site and explore, learn about the Littelfuse sensor products by looking for application guides as well as sensor catalogs and reed switch cross reference tool.
This has been a great discussion for me, Julius. Can you summarize it for all of us that are listening?
Of course. So I would like to define the key points for takeaway. So Littelfuse is a leading manufacturer of the reed switch in the market. As well, Littelfuse provides magnetic sensor based on reed Hall technology. Reed switch is simple and reliable choice for extensive variety of applications. And the last one, magnetic sensor provides differentiated benefits and features for selected applications.
All right, thank you, Julius. So this was very informative to me, and I really appreciate the animations and also those kind of takeaway slides that show the side by side comparison of the attributes and the applications. I think our engineers are going to find that very helpful.
Yes, I appreciate the time and looking forward for next discussion with you.
That sounds great. And before we sign off, I want to thank our Tech Chat sponsor, Mouser Electronics. If you appreciate this Tech Chat, go ahead and check out their website when you're looking for electronics parts and components, including Littelfuse, our guest today, and their magnetic sensors. So until next time, thanks for joining us on Tech Chat.